Let us see what is the unit of stress. Right, stress is your force per unit area. So the unit of force is Newton, SI unit of force is Newton, and SI unit of area is meter square. So the SI unit of your force is Newton per meter square, and we know that 1 Newton per meter square is 1 megapascal, and I already told you that 1 Newton per mm square is 1 megapascal. Just remember, because in strength of material every dimensions will be given in mm, every properties of metal will be given in your gigapascal or something like that. So we have to deal with megapascal frequently. So 1 Newton per mm square is 1 megapascal, and if in the question it is given that the unit in CGS unit, that is 1 kgf per centimeter square, so you can say 1 kgf per centimeter square is 0.1 megapascal. These conversion you must know to solve the numerical, and 1 kg force is equal to 10 Newton. So this conversion is very important. When it is for the question, you must know all these things. The next is your strength. What do we mean by the strength of a material? We already see that stress is the internal resisting force developed in a member or developed at a point against the deformation when you apply some external load, and that deformation must be resisted. But strength is the maximum or limiting value of stress that a material can withstand without failure or fracture. Right? How much is the maximum amount of stress a body can withstand without failure or fracture? That maximum amount of stress is known as your strength. Right? So there are two types of failure in your strength of material. One is your failure, or you can say one is your yielding. When we will see also this when we see the stress strain diagram, when because of some load, because of some stress, if the member is deformed and that deformation is permanent, right? Suppose if I apply a load on this in this direction, its length will increase, and if I remove the load, this length will regain its original position. Then we can say that this deformation is not permanent. This is up to the level when you apply the load, deformation is there. When you remove the load, deformation will not be there. But at a point when this load or this stress is so high that the deformation caused in this marker or in this body is permanent, then in strength of material we can say that it will cross its elastic limit and body will fail. Right? In strength of material we are dealing with the yielding point where the body will gain a permanent deformation, then we can say the body will fail. And there is another failure which we known as fracture. Fracture means that what is the maximum amount of stress this body can withstand without break. When this body will break, that breaking point is known as fracture. This body will fracture. So there are two types of strength. One is your yield strength, that is SYT. SYT is yield strength under tensile load. When you are applying a tensile load in this, then what is the yield strength of this marker or of this material? That is SYT, yield strength in tension. There is a term SYC, that is yield strength in compression. Right? So we can say if the stress which is induced in the body is greater than its yielding strength, then you can say that yielding will be there, yielding occur. What do we mean by yielding? That there is some permanent deformation. Permanent deformation will be there. So we can say body will fail. And if I say that if the induced stress induced stress will be greater than SUT. SUT is your ultimate strength during tension, right? SUT is ultimate strength during tension. So if this is greater than SUT, we can say that your body will fracture. Body will fracture, right? This is the case of fracture and this is the case of failure. In strength of material, we are dealing with the failure, not fracture. Fracture will be studied in your theory of plasticity, but in strength of material, up to the level of our GATE or engineering services, we are only concerned about theory of elasticity, that the stress will be within the elastic limit, it will not cross the elastic limit, then there must not be the permanent deformation, right? So from here I can write that your stress is a variable parameter, right? Stress is a variable parameter. It will vary. It depends upon the how much load you are applying on the body. When you are increasing the load, then the stress will increase, right? It is a variable parameter, but your strength is a constant parameter. Strength of a material is a constant parameter, right? Its value is constant and it is a property of material. It is a property of material. For every material, the value of SYT and SUT will be constant. That is the maximum stress that material can withstand without your fracture or without yielding, right? So this is the meaning of strength. We also say that the stress is a tensor quantity. Let us say, what do we mean by tensor quantity? There are three quantities present in the physics if you study. That scalar quantity are those quantities which are having only magnitude. No direction is there. For example, speed, right, which have only magnitude. Vector quantities are those quantities which are having magnitude and one direction. Those quantities which are having magnitude and one direction is your vector quantity. For example, velocity, acceleration, force, momentum, right? So much quantities are there which are vector quantities. Tensor quantities are those quantities which are having magnitude and more than one direction. For example, your stress. Stress is a tensor quantity which are having more than one direction. How? If you can say. So from here you see one thing, that is scalar is a zero order tensor and vector is a one order tensor, right? So okay, leave it. We can say that how the stress is a vector quantity. We say that stress is your force per unit area, right? Stress is your force per unit area. This force is having one direction, right? This force is having one direction, and now we have area. We say that your stress is defined at a point and area is a vector quantity with respect to a point. So for in any member, if you want to calculate, suppose I can say that, let us say this is the member or this is the body, I want to calculate stress at this point. So from this point, number of planes are going, like this plane, number of planes are passing from this point. So each planes have its own direction. So that's why area is a vector quantity for a point. But area is a vector quantity with respect to a plane. If I am talking about what is the area of this plane, the area of this plane is this one, which you can see, and this is your scalar quantity. But area is a vector quantity with respect to a point. So we can say that because this area is also having one direction, this area is also having one direction, so the stress is having two directions, one is of force and one is of area, right? Stress is having two directions, one is of force and one is of area. That's why your stress is a tensor quantity, right? Now let us solve for the case when you want to calculate the stress at different planes passing through a point. We will see, we already studied that your stress at a point in all the direction is not equal, just like your pressure. Stress at a point in all the direction is not equal, just like pressure. Let us find how it is possible and what is the magnitude of stress at different planes. So the heading will be expression for normal and shear stress, that is sigma n is normal, tau s is shear stress on a oblique plane under axial loading. When a body is under axial load, what is the value of this? Your oblique plane, what is the value of normal stress and shear stress? Now let us consider this is a member, this is a body. The cross section of this member is your circle of diameter d. So area of cross section is pi by 4 d square, right? If I can say the axis, this is your x axis, this is y and this is z. In x axis I applied a tensile load P, axial tensile load P. Now suppose we have the cross section, section 1 is the section of cross section, 1 is a cross section. So I want to know what is the value of stress on a oblique plane. This is 2 2. This blue color plane is the oblique plane, which is at an angle theta from the plane of cross section. Theta is the angle between plane of cross section and the oblique plane. And if I say that A is the area of cross section or area of section 1 1 and A dash is the area of section 2 2, right? This plane has another area, the area of this plane is different. So from this, if I can say this area is A dash, this area is A, so I can write A upon A dash is cos theta, right? The area of this plane, this is this area, A upon A dash, this area is cos theta. Let us say this is your equation number 1. Now I want to know what is the value of normal stress and shear stress on this oblique plane. I am considering let, because of this load P, the normal load on this plane 2 2 or on this section 2 2 is, let us say, Pn. This Pn is a load perpendicular to this cross section, so it will be act as a normal load, and this component of this P in this direction is parallel to the cross section. This is parallel to the cross section and it will act as a shear load. So that's why I am writing S and N here, right? So if you can say that, if you define your theta in this case, so if I can write here that one thing, that what is the stresses on plane of cross section. This is the plane of cross section 1 1. So what are the different stresses at plane of cross section is, on plane of cross section normal load which is perpendicular to the cross section is P, and shear load which is parallel to the cross section is 0. There is no shear load in this plane, so the shear load will be 0. So I can write the normal stress on the plane of cross section 1 will be equal to normal load on section 1 divided by area of section 1, that is P by A is the normal stress on the cross section plane. This is equation number 2 if I can write. Now the shear stress will be shear force upon area. Shear force is 0, so this tau s will be 0. These are the stresses on section 1. Now we have to find what is the stresses with respect to oblique plane. With respect to oblique plane, we have to find the stresses. So with respect to oblique plane, we have to first find what is the value of this Pn and this Ps. So if you can say from this, if I can write that this is the angle theta, right? This is the angle theta. So this angle must be theta. This angle must be theta. How you can say that this Pn is perpendicular to this plane, right? This Pn is perpendicular to this 2, and this axis, longitudinal axis, is perpendicular to 1. So the angle between 1 and 2 is theta. So the angle between their perpendiculars, that is this line Pn and this longitudinal axis, must be theta, right? So if P is acting in this longitudinal axis in this direction, so the component of this P in this direction will be P cos theta. So Pn will be P cos theta, and the component of this P in this direction will be P sin theta. We know how to resolve the components or vectors. So this is P sin theta, right? It is P cos theta and P sin theta. Because, and this is possible only when this force is a vector quantity. That's why we are resolving this force in different directions. So if you want to write what is the normal stress on the oblique plane, that is sigma 2 will be equal to, if you can say normal stress on oblique plane, that is normal load on oblique plane divided by area of oblique plane. Divided by area of oblique plane if you are considering oblique planes. So what is the normal load at oblique plane is P cos theta. What is the area of oblique plane? A dash. This will be equal to P cos theta upon, what is the value of A dash? A dash is A upon cos theta. This is A upon cos theta. So from here you can write sigma n at point 2 will be equal to P by A. This cos theta will go on numerator, cos square theta, and this P by A is sigma n at the section, right? P by A is your sigma n at the section, or you can write this as sigma, if I can denote it as a sigma, right? If I can write it as a sigma, so I can write sigma n at the section 2 is sigma into cos square theta. Sigma into cos square theta. Sigma is the normal stress on the plane of cross section. If I write here, sigma is normal stress on plane of cross section. This is sigma cos square theta. This is the normal stress on this oblique plane. Now if I want to now find what is the shear stress on oblique plane 2, it will be equal to shear force upon area of oblique plane A dash. Shear force will be equal to P sin theta. We already calculated P sin theta. A dash is A upon cos theta. So it will be equal to P upon A sin theta cos theta P by A sine theta cos theta. So you can write from here tau s on section 2 will be equal to P by A is sigma into sine theta into cos theta is sine 2 theta by 2. Sine 2 theta by 2. This is the shear stress on oblique plane. That is the shear stress on oblique plane. So on the oblique plane, the normal stress will be sigma cos square theta and the shear stress will be sigma sine 2 theta by 2. Now if you can visualize the things, we are only applying a normal load. P is a normal load. So I can say that on the section, on this cross section, only normal stress will be there. But other than this cross section, at each and every plane passing through this, at each and every theta, we have shear stress also, right? So it is not like that you are applying a axial load or a normal load, then only normal stress will induce. That normal stress will only be at the cross section. At the section shear stress is 0, but other than the cross section, at each and every theta, at each and every plane, there must be a shear stress also, right? So any oblique plane at any theta, both normal stress and shear stress will be there, right? Both normal stress and shear stress will be there. Now if you want to find what is the maximum normal stress, if you want to find what is the maximum normal stress, so the normal stress is sigma cos square theta. The maximum value of cos theta is 1. So if I can say the sigma n maximum will be equal to sigma when your theta is 0. Cos 0 is 1. When this is cos, when this is applicable when theta will be 0 degree. Theta is equal to 0 degree means that theta is 0 means plane of cross section. Plane of cross section. So you can say that in this case, in uniaxial case, the maximum normal stress will develop at a section or at cross section, and you know that at the cross section shear stress will be 0. So the first conclusion from this derivation is that we will also see this in your combined stresses and strains or your Mohr circle, but right now for the uniaxial case I am just saying some conclusions now, that sigma is the maximum at the plane of cross section, or in any member normal stress is maximum at that point or at that plane where shear stress is 0. Where shear stress is 0. At this theta is equal to 0, our shear stress is 0. So the condition, if I write here the conditions for the maximum values, if I write here the condition of the maximum values, so I can write sigma n is maximum at that point, at that plane or point, if you are talking about stress, so at that point where shear stress is 0. Where shear stress is 0. This is the most important condition of normal stress, maximum normal stress. So at sigma n is maximum, so it implies that at that plane or at that point shear stress is 0. This is the most important thing. Most important thing. Just remember this thing. We will also see this later on, but right now one conclusion you can make, that normal stress is maximum where shear stress is 0. If you want to find what is the maximum shear stress. What is the maximum shear stress? So I can say that the shear stress magnitude is, shear stress will be equal to sigma by 2 into sine 2 theta. For maximum, the value of sine theta maximum will be 1. Right? So for maximum, if I can write, for maximum, this 2 theta value will be equal to what? This 2 theta value will be equal to 90 degree. Right? Theta will be 45. Theta will be 45 degree. Right? At sine 91, so this 2 theta will be 90, so theta will be 45. So I can say that shear stress is maximum value is equal to sigma by 2 at a plane which is at a 45 degree from the cross section. Which is at a 45 degree from the cross section. Right? At a 45 degree of this cross section, in this plane, your shear stress is maximum. And if you can find what is the magnitude of normal stress when theta is 45, just find out what is the magnitude of this normal stress when theta is 45. So this will be equal to sigma into cos square 45. Cos 45 is, right, what is the value of cos 45? You can know what is the value of cos 45 is 1 by under root 2, right? So cos square 45 is 1 by 2. So you can write sigma n at theta is equal to 45 degree will be sigma by 2. It is not 0. That means that second important conclusion from this is that where shear stress is maximum, at that point normal stress cannot be equal to 0. Normal stress cannot be equal to 0. But where normal stress is maximum, then shear stress must be 0, but the reverse is not true. Where shear stress is maximum, normal stress cannot be equal to 0. It has some value, right? It cannot be equal to 0. So you can say one thing also, that at a plane where normal stress is maximum, that implies that shear stress is 0. So these are the planes of pure normal stress. This is the plane of pure normal stress. Means at this plane, at the cross section plane, or at the plane where normal stress is maximum, that plane is known as pure normal stress plane. And we will say later on, these planes are known as principal planes, where normal stress is maximum but shear stress is 0. Right? Only normal stress will be there, no shear stress. But in this case, where shear stress is maximum, in this case normal stress is not 0. So I can say that this is not the plane of pure shear. Right? It means in the plane of pure shear, third conclusion, in the plane of pure shear, where there must be a plane, see, one thing is there, at this point n number of planes at n number of thetas are present. From 0 to 360, n number of planes are there. So there must be a plane where this value is 0. Where this value is 0? At cos 90. This value is 0 at 90 degree. Right? So at 90 degree, this is not 0. Right? So where normal stress is 0, shear stress is not equal to 0, those planes are known as plane of pure shear. Plane of pure shear means only shear stress, no normal stress. Plane of pure normal means only normal stress, no shear stress. right? So plane of pure normal means normal stress is maximum, shear stress is 0, but plane of pure shear means, or plane of pure shear means your shear stress is not equal to 0, but normal stress is 0, but the magnitude of that shear stress in plane of pure shear, shear stress has some value, that value is not equal to your tau s maximum, right? That is not maximum shear stress, because at the plane of maximum shear stress, at the plane of maximum shear stress, your normal stress is not equal to 0. This is not the condition of plane or pure shear stress. At the pure shear stress condition, your shear stress is not equal to 0, normal stress is 0, but that shear stress is not maximum. Not like this, that in plane of pure normal, normal is maximum, but in plane of pure shear, shear is not maximum. Just remember these conclusions. This will help you to solve the numerical very easily, right, in your GATE exam. Don't need to derive all these equations. With the help of these conclusions, you will directly rush towards the answer and directly write the answer, that and the plane of pure normal, normal stress is maximum, shear stress is 0. In the plane of pure shear, shear stress is not 0, normal stress is 0, but shear stress is not maximum. And in the plane of maximum shear stress, your shear stress is maximum, but normal stress is not equal to 0. These are the conclusions which we can derive from this equation, right? These are the very, very important conclusions. You can write or you can note it down. So if I can say that from this we have some conclusions for pure normal, pure shear, maximum normal, maximum shear stress. Some other conclusions also we can say that we can find out from these equations, we can find out normal stress and shear stress and any oblique plane, because theta is there, at any theta you can find normal stress and shear stress passing through a point under uniaxial state of stress. These formulas are only valid for uniaxial loading. Only axial load is only applied on one axis, that is x-axis. That means in this case your sigma y and sigma z both are 0. Only pure axial, only uniaxial condition is there, y and z sigma will be 0. So it is not, this is only applicable for uniaxial state of axial loading. That's it. We can also determine what is the maximum normal stress and maximum shear stress, and that these maximum normal stress and maximum shear stress can be helpful in your design condition. When you want to design, then you need what is the maximum stress developed, what is the maximum normal stress, what is the maximum shear stress developed. You need to define this. So with the help of these equations, you can be able to define what is the maximum value of normal and shear stress, right? And also we can in this we will be able to determine where is the plane of pure shear, where is the plane of pure normal, and what are the conditions of plane pure shear and pure normal stresses, right?